Hey there, this is lesson 15, Paleomagicians. Last time we talked about pillow basalts that are found at mid-ocean ridges and how they're kind of strange rocks. They're these heavy, glassy, rinded black rocks that seem to indicate underwater volcanic eruption. They have another interesting property though, and that's that they're quite strongly magnetic, certainly enough to deflect a compass. Of course, when scientists found this out, they want to know everything about that magnetism. How far does it reach? What's the polarity of it? And just where does this occur? So the initial thing is to map it, do a geomagnetic survey. And that's exactly what happened. By about 1960, Raff and Mason published quite an interesting paper of a number of surveys. Actually, they had tied together and linked up to create a large geomagnetic survey off of the Pacific coast of North America, so just off of Vancouver Island and Vancouver. What they found was a really weird repeating sort of pattern of zebra stripes, and what those are magnetic polarity. So black is normal polarity, where the magnetic North Pole was roughly north, where it is currently. Raff and Mason presented this, but they didn't really have an answer as to how such a thing could come about. There was definitely some sort of striking pattern there, but just what it meant was they didn't have it. A fellow named Fred Vine at Stanford in the 60s was doing his PhD on this very subject. He was a big believer in continental drift, and luckily he had pretty expert guidance. Some fantastic geologists and oceanographers, I suppose you'd call it, were also helping him, Drummond Matthews and Larry Morley. They all were aware of this theory of continental drift, and they were trying to apply that to this interesting pattern. They knew that since the 20s or so, it was sort of common knowledge that rocks can crystallize and align their magnetic polarity with magnetic north on Earth. So you can actually sort of date rocks or relatively date them based on their magnetic polarity, because of course the magnetic polarity on Earth isn't fixed. It's to do with the geodynamo in the center of the Earth. And every once in a while, every number of thousands of years, it actually reverses. And even when it's not reversing, it actually wanders. And that's why you have to account for declination changing on maps if you navigate with a compass. Anyway, so Vine, Matthews, and Morley are studying the previous sort of zebra striping of magnetic polarity off the Pacific coast of North America. And they applied this idea that Earth's magnetism or magnetic north has reversed over time, and they tried to apply the time scale that existed to the magnetic polarities they were seeing off of the coast. And when they did this, it all clicked. They found that the young rocks were in perfect symmetry outwards with older rocks. Right at that mid-ocean ridge were the very youngest rocks, and progressively outwards on both sides, just in perfect symmetry, like a butterfly wing, rocks are getting older. This was proof that new rock is being created at a mid-ocean ridge, and that the seafloor is spreading and recording Earth's magnetic polarity, just like a tape recorder. The discovery of seafloor spreading wasn't trivial. This was a big deal, and it's probably the biggest discovery ever in earth science and geology, because it ties together so many mysterious aspects, like all those fossil bands, the glacial tillites at the equator, coal beds in Antarctica, the jigsaw fit of the continents, and ultimately continental drift finally has a mechanism in seafloor spreading. Luckily, built in is sort of a test for how fast this happens as well, because of course that's another big question. Just how long does it take for the seafloor to spread? Well, if you look at the ages of this paleomagnetic data, when these magnetic reversals happened and how they're recorded around a seafloor spreading center, well, we find that it takes, it's about 1 to 10 centimeters per year. And to put that in some kind of perspective, 100 meters traveling at the speed of seafloor spreading takes about 10,000 years. So let's look at the scale of this. If you look at the Pacific Ocean and imagine that at one time it didn't exist. The entire Pacific has been created by seafloor spreading. And so if you imagine 100 meters taking 10,000 years, and we look at the scale of the Pacific Ocean, it's pretty impressive. Remember, all of human history is basically contained in 10,000 years. And that only accounts for 100 meters of this Pacific Ocean seafloor spreading. I find that pretty humbling. As always in life and science, when you answer one big question, it often leads to another bunch of questions. And that's exactly what happened here, because now that we know the seafloor is in fact spreading, it's pushing the continents around the globe, and the Pacific and the Atlantic are getting bigger. That makes a space problem, because this new rock spreading out means there's not enough room for the old rock. So where does all that old rock go? And that's a question we'll try and answer in the next lectures.